and you're good to go. Over to you, Karen.
All right. Well, thank you so much for having me. It's a real honor to be here. Really many thanks to the IGS for everything that you all do. So I'm going to talk today about something that caught my interest a while back and just doesn't seem to let go of it, because we just keep finding more interesting things to look at with basal channels. So what I'm going to try to do today is give you kind of an overview of, what channels are, where we find them, and bring in a lot of the other literature on basal channels. It's a fairly young study, honestly. I don't think there's been a lot of work for a long time on these, but there's been a lot recently, which is fabulous. And so I'll tell you right now, I'm not going to get everybody into this, and I certainly owe a lot more authors than I'll be able to bring up here for a really broad understanding of these features. And there's lots more left to do. So I'll try to give you an overview and then work in kind of some previews into some projects that we're working on these right now. So we'll start with the basics here. What are basal channels for those of you who aren't familiar with these? So let's first start on the surface of the Earth, which is something we're probably a little more familiar with than the undersides of ice shelves. So this is a hill slope on the surface of the Earth. And if we have rain that falls on a hill slope, if there's enough of it at least, it tends to channelize, right? It get a little sheet wash, but it tends to find the low spots and it accumulates in the low spots. And as it goes, it makes the low spots lower as it erodes that hill slope. Ice shelves are kind of like upside down hill slopes, right? So on hill slopes, we get rain on the surface that flows down. Underneath ice shelves, we get water that melts near the grounding line, near the base of the ice shelf. And that's fresh water that melts, so it's more buoyant than the salt water around it, and it rises along the base of the ice shelf. And just like channels on the surface flow into the low spots and tend to make those low spots lower, channels on the undersides of ice shelves tend to flow into the high spots and make those high spots higher. We have melting rather than erosion of material, but it's kind of a similar idea. So in a way, when we look at basal channels, what we're really looking at are these upside down rivers that form underneath ice shelves. If you have a big upside down river on the underside of an ice shelf that has melted through and made those high spots higher, the top tends to sag in. And so we're able to see these from optical satellite imagery. These right here that we're looking at in this picture, this is the Venable ice shelf. So the bumpy stuff over here is grounded ice. The red line there is the grounding line from the Motus Mosaic of Antarctica. And then the kind of smoother stuff out here is the floating ice. Black is the ocean. We've got ice flow basically going from right to left here. And we see some markings that are kind of perpendicular to ice flow, and those are fractures. But these features that are closer to parallel to ice flow, although with some deviation from that, those are our basal channels. So that's where we've had the big stuff being carved out underneath and the top is sagging in. These are big features, and the ones that we see on the surface, it needs to be wide enough for that sagging to occur. Otherwise, the stresses just from the ice shelf hold it up. So they need to be large enough for that bending to occur if we're going to see them in optical satellite imagery. But these tend to be something like 1 to 5 kilometers across that we're looking at. So it's easy, I think, to forget looking at satellite imagery just how big these features are that we're looking at. So they're upside down rivers, but they're very large upside down rivers. So when we started really looking at these, the first thing we really set out to do was to come up with a mapping of where we find these features in Antarctica. And we've used a few different methods, and other people working on these have used a few different methods as well to map these features. Mostly what we've used is optical imagery, since especially the big ones are visible in optical imagery. That's our best bet for kind of the longest term record that we have available to us. It's lucky we can see them there. DEMs are even better. So then we're not dealing with shadows and things that can make it harder to pick out those channels. So things like REMA are really, really valuable for picking these out now. These are awesome in ice penetrating radar. There's lots we can use from there. And we tried to do a lot of kind of validation using ice penetrating radar. Problem is, it's not available everywhere. So what we did was we mapped using optical imagery, and then anywhere we could, we checked using ice penetrating radar to really see if there was a channel on the base of the shelf. And it was 100%. Everywhere we thought we saw a channel, there certainly was a feature on the base of the shelf. There might be different explanations for how it formed, but there was at least something there. And then we used persistent polynyas, which I'm going to talk about in a little bit more detail in a minute. This is kind of what we got for the distribution of these channel features around on floating ice shelves around Antarctica. What you're looking at here with these dots is every dot represents 50 kilometers of channel length. So it's giving you an idea here of where they are and also kind of the density of, how long they are, how much of the ice shelf they tend to take up. You'll notice in this that there's some different colors that I've used on here, and that's because it seems like there's some different types of basal channels. And I think our understanding is evolving pretty quickly right now and may challenge some of these categories that we've put in. But for now, they seem like they're at least working to give us a start. So let's look at 3 different examples of these different types. So we'll start here on the Ronny ice shelf. We'll move over to the Venable, which we just saw, and then down to the Salzburger to see these kind of 3 different types of channels. So this is on the Ronny ice shelf. And again, same thing here. We've got bumpy stuff is grounded ice, smoother stuff is floating ice, and the red there is the MOA grounding line. And you can see that there's a basal channel here that kind of forms right at the grounding line, and it kind of peters out as it moves towards the ice edge. The ice edge is somewhere off the left of this image. And this is what we call subglacially sourced channels. So these have been mapped by other people. Anne Lebrock had a really nice paper on this where they compared places where there's modeled hydrologic outflow with where these channel features start. They match up really, really beautifully. So what's happening here is we have some concentrated subglacial meltwater outflow. And again, that's fresh water. So we're putting a source of fresh water right at the grounding line. That is rising along the base of the ice shelf with that buoyant energy it has. And then you'll notice, at least in this situation where the water under the ice shelf is pretty cold, eventually, basically that water super freezes, it super cools and it freezes. And you eventually see that basal channel kind of disappear as you move towards the ice edge. So those are subglacially sourced channels. And we put those in contrast to what we called ocean sourced channels. And ocean source channels don't form right at the grounding line. So you'll notice on that last one, that channel connects directly to that grounding line. We don't see that with ocean source channels. They often come pretty close to the grounding line, but there's a bit of a separation between the grounding line and where we see the head of that channel begin. And maybe more significantly, it's really common to see these ocean source channels deepening as they go towards the ice edge. So that might have to do with changes in ice thickness. It might also have to do with the plume that's driving this channel. What we have for our kind of conceptual idea of how these form is that we get, in particular, we see these in areas where we do have lots of warm water near the grounding line. So we get melt near the grounding line, which is our fresh, buoyant fresh water that wants to rise, but it's also mixed with relatively warm water. And so if you mix relatively warm with very fresh water, that might add more energy to that buoyant plume, which will carve more energetically as it rises and be less likely to super cool. So those tend to reach the ice edge at least in many situations. We see that commonly. And then the last one, we gave it one more category, which is just kind of something somewhere in between. These ones are harder to classify. We call these grounding line source channels. And these tend to start at a grounding line, whether that is the main grounding line or perhaps the grounding line of an island, for example, like this channel here on the Salzburger ice shelf. Seems like it starts at a grounding line, but it's not an area where we have modeled subglacial outflow. So it's possible in some of these situations that we're missing it in the models. Perhaps we don't have the right bed topography in detail there, and so we just haven't modeled that subglacial outflow. They might be subglacially sourced channels. In other situations, it might be the same drivers as ocean source channels. It's just that there's a shallower grounding line. And so we tend to see the expression of that channel closer to the grounding line. So there's some end members, and then there's kind of something in between, which there's a lot more interest left to figure out how those form. We do notice with these features in general that there is a positive correlation between basal channel density and basal melt rate. My guess is just looking at the mapping, you can kind of see that visually. I've put ocean bottom temperatures on here. And so in those areas where we tend to have a lot of circumpolar deep water, we tend to have a lot of channels, especially ocean source channels. And so we do see that positive correlation. We do see a significantly higher density of channels in the Amundsen and Bellingshausen seas than anywhere else. And we also, interestingly, see a positive correlation between the density of basal channels on an ice shelf and the grounding line depth in the Amundsen and Bellingshausen seas sectors. So what that's saying is, okay, in places we know that there's circumpolar deep water, which we know is a fairly deep water mass and is likely to drive those channels forming with warm water. We know in the areas where that exists that the deeper the ice shelf, the more basal channels, which is really just a proxy for the more interaction that ice shelf has with circumpolar deep water, the more basal channels we tend to see. And it's important to remember in this that we're really still just talking about large basal channels because we're using mainly optical imagery to map these channels. Again, they need to be big enough for the hydrostatic adjustment to cause it to sag on the surface. So we're really just looking at large basal channels. I don't know if these ideas hold when we're talking about smaller basal channels because we don't have the data to map those well. But at least with large basal channels, we do see this strong relationship between warm water tends to indicate more of these big basal channels. Another thing we noticed when we were mapping these is that channels tend to disproportionately form in shear margins. We see a lot of these channels forming right along shear margins. But one really big challenge we were having with that is that shear margins are really messy. So if we're looking at basal channels and trying to identify them from optical imagery on the surface, in some places, like there's one right here that we can see quite clearly, but while there might be a basal channel under this shear margin or under this shear margin, right, it's hard to see just from the surface. But there is something else that can tell us whether there's a channel there without having to sort out those crazy shear margins. And that's these persistent polynyas that I mentioned. So a polynya is an open water area. And what we're defining in this case as a persistent polynya is a small area of open water that forms right at the end of an ice shelf, and it stays in the same spot relative to the ice shelf edge year after year. And these are something that we can see really well when there's fast ice, sea ice present, and we can also actually see even thermal imagery as well, which is something we're working on. So this is a hard image to look at. There's a lot going on in here. This is Thwaites Glacier that we're looking at. Here's the eastern ice shelf over here, the western ice tongue, which is mostly disintegrated by now. Grounded ice is on the bottom, and then here, this time in black, is our grounding line. And what I've done here is I've overlaid shear strain rates in red. So the dark red areas are marking a shear margin. A lot of these are kind of spurious correlations because as you'll see in a moment, these things change very rapidly. So what I want you to start with is to focus on this area right here. So this is fast ice. This super smooth stuff out here is fast ice. Black is ocean. And it's a little hard to see. It'll be easier in a moment, but we see the ice edge right in here of the eastern ice shelf. And right there at the end of the ice shelf is a persistent polynya. And I'm going to go through a series of MODIS images here, and there's lots going on. But if you keep your eye in that area, it's a little dark sometimes. When there's fast ice present, you can see that polynya forming in the same spot. There it is again. I can't really point and move this over and over. So I'm hoping you see that in there, how that keeps forming in the same place. You can like almost see, it almost looks like there's water, kind of bubbling up and keeping the fast ice separate there. So we see those, this is not a shear margin over here, right? We don't see high shear strain rates in this area, although this is a basal channel, and that polynya forms at the end of a basal channel. We do see one though that forms at the end of the shear margin. Now this is a bit of a mess. Like I said, shear margins are messy, but we can see around that same area, we keep getting these little polynyas that opens up. And this is a messier area, and it gets really messy when right about there, the Western ice tongue disintegrates in kind of the mid-2000s. But I think this is a good example to show you, just how complicated this area, these shear margins can be. But if we can identify a polynya that's showing up in the same place relative to the ice edge over and over and over, it's a pretty good indication that we have some mechanism that's consistently delivering plumes of water to that location over and over and over. And the easiest mechanism, the only mechanism that we've come up with that consistently could control that is the presence of basal channels. And often we can see them, often they're also visible on the surface. But those persistent polynyas really give us a good idea that there's channelized melt happening underneath the ice shelf that's delivering a plume with enough buoyant energy that it rises directly vertically as soon as it exits the ice shelf cavity. So these are examples of other places where we see these basal channels forming in shear margins. So again, I've overlaid shear strain rates in red here, so you can see some of those concentrations of high shear strain rates. Those shear strain rates don't necessarily come from the same time as these images, so some of the ice edges don't quite match up. But you can see lots of places here where we have polynyas that we find in shear margins all around Antarctica. So this is something that's really common. We mapped all the persistent polynyas that we can find using the MODIS Ice Shelf Image Archive. So this is all the ones that we found, and that persisted in the same location. I think we said for 3 or more years was the criteria that we used. So there might be more that we just haven't had enough fast ice to be able to see them. But what we found is we found 33 of these, and of those 33, 18 of those form in shear margins. And so with our observations of channels in general, and certainly with our observations of where we find these persistent polynyas, it seems to indicate that we have more channels and shear margins than you would expect just based on an area average of where you might get these channels. So we dug into that a little bit, thinking about why we might get channels disproportionately in shear margins. And I think the answer to this really starts on grounded ice. So we used the reference elevation model of Antarctica, REMA, to figure out what the surface elevation was doing in shear margins on grounded ice. And what we found is that there are big dips in shear margins on grounded ice. And my guess is that is not a surprise to many of you. I've talked to people who've been in the field near shear margins who remember, seeing a big dip in the shear margins. But it's really big. And on fast flowing ice streams in particular, you get really big dips in the shear margins, up to about 100 meters of relief in those shear margins. And the reason that we get this is really just basic ice dynamics. So we've got over here, this is Pine Island Glacier with Pine Island Ice Shelf, and I've drawn some streamlines on there and also put the shear strain rates again in red so you can see those shear margins. So if you imagine a parcel of ice that comes from outside a shear margin and enters a shear margin, it's going from flowing slowly to flowing very quickly. And when it does that, it has to stretch and thin to accommodate that acceleration across the shear margin. A parcel of ice that flows right down the middle of that ice stream never crosses a shear margin. It never goes through that big velocity gradient that would really stretch it and thin it. And so what ends up happening, if you imagine a cross section now across one of these shear margins, what ends up happening is ice that's sitting on the outside hasn't been stretched, so it's thick. And ice that's inside the shear margin, so this is the left lateral shear margin here, ice that's inside hasn't crossed a shear margin, so it's thick too. But the stuff that crosses the shear margin is stretched and thinned. And so we tend to get this big dip in elevation across the shear margin. So that's step one. Step two, then, thinking about basal channels are not on grounded ice, right? They're on floating ice, but we can actually see that elevation difference cross over the grounding line and onto the floating ice. So we see some continuity. There's profiles, again, this time we're on the right lateral shear margin here of Pine Island Glacier, because that's what we were on before. And so again, this is floating ice, and there's our shear margin. So this is slow flowing ice outside the ice stream. And you can see that big dip happens above the grounding line, it happens at the grounding line, it happens below the grounding line. And we went and looked at ice shelves all over Antarctica, and where you have that big ditch above the grounding line, it tends to persist across the grounding line. And when it starts floating, that's now a thin spot. And when it hydrostatically adjusts to floating, those thin spots that were sticking down will float up in the middle, and that will end up giving you a high spot on the base of the ice shelf. So we see these basal channels basically trying to find high spots. They're flowing preferentially, just like a stream on the surface of the earth flows down into the low spots and flows downhill. We're seeing these basal channels finding the high spots as they flow uphill, upside down under the ice shelf. And it just happens that those shear margins give them a pretty predictable high spot. So if you have a pretty fast flowing ice stream that has well-developed shear margins, it's likely to be preconditioned for basal channel flow in its shear margins. Doesn't mean that there will be basal channel flow in the shear margins. That depends on whether there's warm water and melt at the grounding line to drive that flow. But it's likely that if there is, it's going to channelize right beneath the shear margins. And I think that's significant, and I'll go a little bit more into that in a moment. So hopefully that gives us an idea. We've gotten kind of what channels are, where we find them, what kind of distribution there is around Antarctica. Another, of course, big topic here is understanding how they change over time. And this is an area, there's been some great work so far, but I think there's a lot of work left to do on this. So I'll talk a little bit about some work that's already been done by our group and by others, and then just a moment on some of the stuff we're working on now. So there's our channel map again. We've got persistent polynyas with those little red triangles that I've added there. And what we're going to do now is go to the Getz ice shelf, which is here in the Amundsen Sea, just kind of around the corner from Thwaites and Dotson. And this is a series of Landsat images on that Getz ice shelf showing one of the types of change that we see, which is headward growth. So again, to orient you here, we've got bumpy stuff on the right, that's grounded ice. Ice is basically flowing right to left. There's a peninsula, this is the Scott Peninsula here. We've got a big island out there. Ocean is just off the images to the left here. This is right near the calving front. And what I want you to look at is this channel right here. So there's all sorts of interesting things going on in this outflow and many basal channels in this image. But I want you to focus in on this channel right here. So this channel in 1986, in this image, that blue line marks the head of the channel where we can really first see that channel upstream. By 2000, that channel had grown upstream to this kind of cyan line. And then by 2014, it was up here on this white line. We haven't seen a whole lot of change since then. But over that time period, that was about 20 kilometers of channel growth upstream. So not a subtle change. This was extending very rapidly upstream during that time. And we were lucky to have an IceSat track that went over near the head of the channel where that growth was occurring, which is this little red line right here. And I'm going to show you the data from that IceSat line. And there's a couple things we're seeing here. So on the left, this is the raw data or the corrected data that I've plotted. And then these black dots, I took a point outside the channel and I collapsed them. I normalized them to that point. The Getz ice shelf overall is thinning on average. So I wanted to take that signal out and just look at what was happening inside the channel. And you can see we're looking here between 2005 and 2007. So we had a few IceSat tracks that went over that. And we can see on the surface that there was a very large deepening signal during that time. And if you use a hydrostatic calculation and you calculate what that means for deepening rate on the underside of the ice shelf, so how fast is it carving straight up into the bottom of the ice shelf, during that time, it was 10 meters a year that it was carving straight up into the base of the ice shelf. Really, really high rates of change that we're seeing there. And it's likely if that channel hasn't hydrostatically adjusted yet, if there's still some bridging stresses that are holding it up, that could be an underestimate. That's not something that we assessed, but it's not likely to be an overestimate of that incision rate. So really, really fast change. This is an exception. We don't see this happening. We don't see that kind of headward growth on lots of channels. I don't think this rate of incision happens commonly, but it does clearly happen. So we know it's possible for channel change to be extremely rapid based on the observations on this channel. Now, headward growth, channel deepening, we do see channels shallowing as well, and we have much more investigation to do on why some channels might be shallowing, why others might be deepening. There's also some ice dynamic response to that that occurs. So we see when a big channel forms, that's enough of a difference in topography to deflect ice flow into the channel. So this has been observed in satellite imagery. This is Reinhard Drew's work on the Roy-Baudouin ice shelf, where he's showing strain rates, convergent strain rates, moving ice flow into the channels. And then Martin Waring et al. Had a really nice paper that just came out recently modeling this kind of flow and showing that in some ways it actually counteracts really fast melt rates. So if that channel is incising into the base of the ice shelf, ice flow is basically trying to fill that channel in so that it kind of modifies those incision rates. So that's an interesting relationship between those two processes that there's a lot more to explore. We're also just in the early stages of trying to understand how channel profiles change over time. And there's a lot of stuff that goes into this, a lot of time spent tracing channels on ice shelves, but we see these channels migrating, they change shape over time. Coriolis is a player in this, which I'll talk more about in a minute. There's interesting interactions with nearby rifts. So all sorts of interesting things that we haven't yet explored in detail, but is worth looking into. So another aspect of basal channels, which is perhaps obvious because it's what drives these channels, is the relationship with basal melt itself. So it is melt from these plumes that are forming these troughs on the base of the ice shelf that cause the top to sag in. And this relationship between how the ocean melts the ice shelf within these basal channels and how the ice shelf melt rates in basal channels relate to overall average ice shelf melt rates is really, really complex. So we see really, really interesting plume dynamics within channels. And we've got a bunch of work going on in the early stages to look at this a little bit more. So first of all, I'm gonna show you some really just stunning images that come from Pierre Dutrot's work in 2016. So this is the underside of Pine Island Glacier. And we see some basal channels here. So we're seeing a couple different basal channels here and then kind of the side of one. And what you'll notice is that they are not smooth. They look pretty smooth on the surface as the hydrostatic effects kind of smooth out the interesting features on the base. But if you look with ground penetrating radar, or better yet, a submarine that can take pictures of these, what you see is really, really complex structures within these channels. And in particular, we see terrace features often in these channels, and our work recently has shown these on Thwaites as well and on Dotson. So these seem to be pretty common features in channels, at least in some warm water areas. And those terrace features are maybe key to really understanding how these channels melt and where that melt is concentrated. So Pierre's work suggested that we have higher basal melt rates on the faces that are closer to vertical and lower basal melt rates on the faces that are closer to horizontal. So a lot of the melt that we see on channels ends up on the sides of the channels rather than being at the apex of each channel, which has interesting implications for how these might evolve, and how meltwater that might be trapped, fresh cold water that might be trapped at the top of these channels, may actually be reducing basal melt rates at the top, and encouraging basal melt rates to the side. Along with those really interesting features on the base, we do see an influence of Coriolis on channel profiles and on channel migration, as I was mentioning. These are just a few profiles across channels. These are surface elevation, but we can see it there as well. And what we see is that the left-hand side, and in the southern hemisphere, the left-hand side of these channels tend to be much steeper. That's the Coriolis favored side, where you tend to get faster plume flow and higher melt rates on that left-hand side. Olga Sergienko modeled this really nicely in 2013, and we do see that in our observations as well of the shape of these channels. The relationship between the channels themselves, the melt in the channels, and the overall average basal melt rates is also very interesting. This is a 2013 paper, Milgate et al., which looked at putting channels into a modeled ice shelf and asking how the overall basal melt rate changed on those ice shelves with those channels added. They did a bunch of other things in the paper too. But this was an interesting figure, which basically said they had some different parameters in here that they changed. But basically what it said is that the more channels you have on the ice shelf, in general, you end up with a lower basal melt rate if you have lots of basal channels. And so basically the idea is that a lot of that plume flow is concentrated within these channels. And since it's concentrated within the channels and not necessarily spread over the whole base of the ice shelf, it doesn't melt quite as efficiently. And so you end up with a lower average basal melt rate. So in that way, these actually might stabilize ice shelves by lowering overall average basal melt rates. Of course, that's balanced with other considerations of those channels as well. We're trying to get a better handle on the plume behaviors in these channels through observations as much as we can. One of those projects, Tasha Snow and Matt Siegfried and others have just gotten funded to look at the polynyas that form at the ends of these channels. And they're interested in doing a lot of the automated detection and analysis of these polynyas to get a better idea of how they change, because those changes may tell us about what the plumes are doing. So Tasha's done a lot of work with this sort of detection, and also with using thermal imagery to look at the temperatures of the plumes that are coming out of these. She's done some great work so far. This is that basal channel that I showed you in the video on Thwaites. So this is the Eastern Thwaites ice shelf. And this polynya right there is at the end of the kind of big basal channel. There's a second one on a smaller basal channel there. And she's been tracking the changes in these polynyas over time and looking at changes in size. And what she sees is a pretty strong seasonal signal. So looking over 7 or 8 years or so and taking kind of the mean of what's been going on there, we see that the polynya appears in the spring. It gets bigger throughout the season, and then either the sea ice breaks out or it disappears in summer or early fall. And so one thing that she's trying to unravel and that we're hoping to do more work with in the future is whether that really is reflective of changes in plume behavior during the season, or whether there's other things like perhaps sea ice thickness that might be affecting that. But we might see a seasonal signal in those plumes. And we're trying to get to that as well using some field observations. So I am very fortunate to be part of the International Thwaites Glacier collaboration. I'm a member of the Tarzan team, which is the Thwaites Amundsen Regional Survey and Network. And we went out in the 2019-2020 season and actually were able to drill through that basal channel that we've been looking at. This is a picture of the Amigos stations. We put one up kind of in the middle of the ice shelf, and then one up in the channel. Ted Scambos is leading those. So we've got some data of the ocean conditions underneath the channel that we're hoping to get some more information out of over time. We also have a team headed back this year right now. The channel station went through kind of hurricane force 4 winds just a couple of months ago. And so they're hoping to get down and get some more data out of that and fix the stations if possible. And we've also been doing a lot of work with radar on those channels. So this is Christian Wild on the Dotson ice shelf. We've been working on Thwaites and on some interesting smaller channels on Dotson. So Christian's been doing AP-res, so point measurements that give us an idea of basal melt over time at one point. Aaron Pettit was leading a lot of work with ice penetrating radar profiles so that we could look at the shapes of those channels, and we're hoping to repeat some of those profiles this season with the crew that's going down. Christian's one of those who's going back down this year. And again, we're seeing really, really high variability, really complex topography, a lot of stuff that we're trying to sort out, that we're hoping that learning about the features of the ice itself will tell us something about how those plumes are behaving as well. So basal channels matter a lot to the basal melt rates and styles going on there. And we're also interested in the structural stability. So there's looking at the melt rates and how that changes on the base of the ice shelf. But then we're also interested in what happens when you put basal channels on ice shelf. How does that interact with flow patterns and with fractures and considerations like that to change the stability of the ice shelf, the structural stability of the ice shelf itself. So back to that stuff I was talking about with shear margins. Remember, we see basal channels very commonly showing up in shear margins. We've mapped those with those polinias pretty confidently. The other thing we know about shear margins is that they're weak spots to begin with. We do see, it's not every ice shelf, but certainly many ice shelves have a pattern where retreat really happens on the shear margins first, and then we see big calving events. So very famously, this happened on Jakobshavn. So this is a picture of Jakobshavn in Greenland in 2001. And what you'll notice is right along those shear margins, you'll probably can see these big fractures that formed on the shear margins. And basically both shear margins had to fracture before the really big calving events happened around that time, before the really big retreat of Jakobshavn took place. There was steady retreat for a long time, but a big acceleration as soon as we saw both shear margins breaking. We saw this pattern. Peterman does this. Peterman, again in Greenland, calves huge icebergs off. Those icebergs calve after we break the shear margins. Pine Island Glacier does this over and over. We've seen Pine Island a few times here. We see fracture along the shear margins, and then we break big icebergs off in the middle with those fractures kind of propagating from those shear margins. These are all ice shelves or ice tongues that are sitting in relatively warm water, but it doesn't have to be. So this is the Rennick ice shelf in East Antarctica, in an area that is, as far as we know, the water is pretty cold in general, but it's the same thing, although this moves much more slowly than the other three ice shelves in this picture. Changes are much slower, but again, we see breaking along the shear margins before we get calving events. So those are just a few examples. We see this in a lot of places. So knowing that basal channels are forming under shear margins, and shear margins are already often a key component to ice shelf stability. They're often the place that breaks first when an ice shelf is retreating. It's certainly trying to understand how those channels are impacting the fracture there and the calving events is something that is important, and something that there's been some good work on already, and I think there's a lot more left to do. We do know that channels can directly cause fracture on the ice shelf surface. So there's a bunch of examples. This is the Roy-Batouan ice shelf again. We see a couple of basal channels here. This is a floating island right there, but you can see that there's been in an area where we've got kind of diverging flow. We do see the channel, the fracture happening along the channels in that situation. David Vaughn did some great modeling work to show that the flexure that's associated with channels, remember what we're doing is carving a trough on the base of the ice shelf, and then the top is sagging in. And when the top sags in, there's a flexural stresses in response to that. And so we end up with kind of fractures on the surface between the channels and fractures at the tops of the channels on the base of the ice shelf due to those flexural stresses. So these are both examples of fractures that are kind of longitudinal fractures. They run along the channels that we're looking at. But we also see associations between channels and transverse fractures, the fractures that go perpendicular to the channels. This is kind of an odd example here. This is back on the Getz ice shelf on the Scott Peninsula. So that channel that was growing headwards is over to the left of the Scott Peninsula. There's two channels that come together at the tip of the Scott Peninsula, and we've watched a big crevassed area form there, which may be related to its interactions with the peninsula itself. But we also see in the middle of ice shelves and also in shear margins, we do see a lot of fractures that are associated with these channels. Exactly how they're associated is a good question. This is Christine Dow's work. Oh, and I apologize, I didn't write it on there, but this is Christine Dow's work and her group looking at the Nansen ice shelf in this paper. But she went and looked at a bunch of different ice shelves, looking at where we have basal channels that connect directly with transverse fractures. And you can see there's a bunch of examples. Often we do see channels in areas that just have lots of transverse fractures, so those may or may not be related. But we also see places where we have channels in areas that there isn't any fracture on the ice shelf except right at the channels. Transverse fractures closely associated with those basal channels. And in this paper, what they found on the Nansen ice shelf is that a channel there is controlling or rifts that are propagating from that channel are causing repeated calving events and kind of controlling when those events happen. So we can see that in isolation there. And this is something that we're continuing to work on to get at a little bit more of the why, trying to understand why these channel features are connected to transverse fractures. Is it that the channels are causing these fractures to form? I think it's actually more likely that they're widening fractures that have been infected from the grounding line. They might also be enhanced by basal melt. So we have a lot of questions that we haven't answered yet. I'd be glad if anybody has ideas, I'd be glad to hear them. But we're working to do a little bit of modeling on those and get into some more detailed observation of a few channels that are spawning these transverse fractures. This is an example here on the left lateral shear margin of Pine Island Glacier. This is 2001, and this is 2018 on the same channel, and another channel that has formed recently. And here it's a little hard to see in that image. But again, we see the growth of transverse fractures that are directly propagating from those basal channels. So that's something that we're working on. We're also interested in how those channels interact with rifts that are already there. So not necessarily rifts that are formed from basal channels, but other rifts on ice shelves. This is back on the Thwaites Eastern Ice Shelf. This is the channel, we drilled through it somewhere up here on the Thwaites Eastern Ice Shelf. And this is a 2001 image on the left. And what's interesting here is there's this whole swarm of big rifts on the kind of grounding line side of that channel, which propagate right through that channel. And then eventually they quit propagating through the channel. And now they stop at the channel, which is a very interesting interaction. And we're now seeing a whole bunch of big rifts opening in the middle of the ice shelf from the other direction. They've opened from this shear zone up here, which are now rapidly approaching that channel. So we're keeping a close eye on how those features might interact with those channels now and in the future. So kind of in summary here, so why do we care about these basal channels? Well, they're kind of everywhere in Antarctica. We do see them in lots and lots of places. We know that they're associated with warm water, right? We see that statistical association that suggests that warm water promotes the formation of large basal channels. So as we see more warm water in Antarctica, we may see more of these features or larger features in the future. We know that they have the potential for very rapid change. We've seen that. We don't know how prominent it is. We don't know what triggered that change on the Getz channel that we were measuring. So there's a lot of questions there, but we know that they can change very rapidly given the right conditions. we know that they impact ice shelf stability, and it's in two directions. We know it's through the modulation of basal melt, which might actually have a stabilizing effect. And we know it's through the structural stability, through changing that, which probably has a destabilizing effect. And we know that we do tend to see these probably destabilizing features forming in these already vulnerable shear margins. So that's something that we need to take a close look at. So thinking about future study on these features, I think there's a lot more work that could be done on channel change over time. I think that's something that we've just really started to dive into. Lots more details of plumes and basal melt patterns. Certainly, I think that as we get more instruments out, are able to drill through more basal channels, or able to get AUVs underneath the ice shelves, we'll learn a lot about that. I'm very interested in how these relate to transverse fractures and what the causal mechanism is there. And then certainly trying to understand in more detail how basal channels might contribute to shear margin failure is certainly a big question for understanding future stability of a lot of these fast flowing ice streams in particular. So with that, I want to say thanks to a whole lot of people. I've put a bunch of names up here. I'm sure I've missed some, but there's a lot of teams that I owe a lot to for this, as well as many people who are working on basal channels. So thank you so much for that. And before I stop talking here, I will put up the slide for next week's lecture. There's 3 earlier career talks and some great topics there. So I hope you will join for that. And with that, I am happy to take questions.
Amazing. Thank you so much, Karen, for that. And as always, please, if you have any questions, indicate that, or just indicate that in the chat, and then you can unmute yourself or put the questions in the chat. I'll check Facebook as well. So there is applause and thanks in the chat, Karen. You probably can't see that right now.
I brought it up. I've got it out here. Thanks very much.
Okay, so there's a question by Felix Hill. Do you want to unmute yourself, Felix, or should I read it out?
Yeah, I can read. So yeah, that was really interesting. I just want to ask, does significant calving caused by the basal channels have any feedback on the basal channels themselves?
I think that's a really excellent question, and I think we have no idea. So in general, I shouldn't say that. There's things we do know. So in general, it seems like again, we're pretty early in our mappings of channel profile change over time, but it seems like the plume locations where these channels are starting is relatively stable. They do move, but they do seem to be relatively stable, and those are close to the grounding line. And so, it'll certainly change where the channels end when you calve off a bit. But it doesn't seem like we've seen yet, like a channel just stop because there was a big calving event. I think it could certainly happen if you get back to where that plume is being sourced. But if you're having those kinds of calving events, my guess is you're also having big grounding line change, which would probably also influence that. We do, though, see big calving events, and we see the polynyas reform after those big calving events. So when we define the persistent polynyas, I always say it's relative to the ice shelf front, because we do every once in a while break off a big piece and the polynya moves way back, but it's still right at the end of that basal channel on the front. So I don't think I've seen any observation yet of a big calving event like fundamentally changing a channel, but I think that there's not enough observations to be really sure of that.
Thank you.
Great, thank you for that. Roland has a question about guest time series.
Oh yeah, I can pull that up.
Great. Fascinating talk, Aaron. In the 2014 image,
Mhm.
I'm not sure if this is just a trick of the light, but that channel seems as though it actually now has a subsidiary sort of ridge running up the middle of it.
Yeah. Yeah, no, it's not a trick of the light. We see that all over. And I have no idea why. So
Yeah.
all I know is I've looked at a lot of channels, and it's a really, really common feature. And it often does seem to develop later, like it's not necessarily there when a channel forms. So that channel that we're looking at on Pine Island Glacier with the transverse rifts is now forming a ridge in the middle as well.
Just to push that further, then I noticed in all three panels, much further to the, I guess it's the east, the channel there has a quite complicated evolution of things coming and then perhaps going again by the time you get to 2014.
Yeah, and one of the things that, and again, if you've got ideas, I'd love to hear them, because I have no idea why these ridges form. But again, they're very common. One thought I have is that, with surface rivers, we often talk about rejuvenating. Ocean side of the tar sands, because I'm not working on those. But yeah, stay tuned for those for sure.
Cool, thanks. Is it all right if I unmute and ask a follow-up?
Yeah, go for it.
Okay, yeah, I'm interested in thinking and hearing your thoughts about how to better measure the flow of the water below or that's entrained in the channels.
Yeah, Allison, we should talk at some point. Didn't have She's done some great work on that gets channel as well. So yeah, we should definitely follow up with some of that. It's a good question. And right now I think that if we can get instruments underneath, one of the things we're seeing with those polynyas is that there's likely some seasonal signal in these channels. So we might get change over time. And certainly I think the more measurements we take under and around ice shelves, the more we realize that we need lots of measurements, because there's so much change over time. So putting instruments in that can give us, point measurements, but give us that time series, I personally think those would be the most interesting to get right now. It's a lot of investment, a lot of work, but that would be the direction I'd certainly want to pursue.
Great. We have another one by Julia Wellner, and she asks, some of the channels you discussed sit on what is probably pretty shallow water. Does it matter as the cavity gets smaller and smaller? In other words, does a small cavity limit the ability of these patterns you described to develop?
Yeah, good question. And one, I apologize for doing this, but once again, the answer is, yeah, we don't have enough observations to say that. I think one thing that does, maybe, assuming our interpretation is correct, points towards that kind of difference we were looking at between ocean source and grounding line source channels. So we do have these channels that seem like they act kind of like ocean source channels. They dip deep towards the ice edge, but they seem to start right at grounding lines. And I think that might be because it is shallower. And so we're just getting that interaction at the grounding line. And certainly, a lot of this is being, as far as we can tell, driven by circumpolar deep water. So if we do have a shallower cavity, that might drive that water up towards the ice shelf base. I certainly think that would matter. On the other hand, if it's really shallow, the circumpolar deep water won't get in to begin with. So I guess those are some thoughts. But yeah, exactly. There's so much more to think about in all of this. Yeah.
Great, thank you. That sounds really, really amazing work. I'm really impressed. Cool. Are there any more questions for Karen? Roger, you have a question / comment?
Yep. Thanks very much, Karen. Very interesting, very inspiring. I was just wondering, you obviously highlighted the mechanical impacts of these channels. I wonder if anybody's done any seismic along these channels to get maybe the more anisotropic mechanical properties. I'm sure the radar imaging was challenging enough with those stepped interfaces to migrate and get good images of, but the seismic would maybe tell you something about the mechanical properties within the ice above those channels. Very interesting, given it's both subsiding and being stressed.
And I think, you know, certainly with the phase sensitive radar, that's something we're hoping to get out of that, is more about the isotropic characteristics. And I don't know a lot about that side. We did run seismics when we were on Thwaites and Dotson, and we were really focused on this is with Atsumoto, he was leading this. And we were really focused on the shape of the cavity underneath the ice shelf. And that's particularly when we were on Dotson, we were trying to hit the hot spots for understanding the ice rises. And so that's what we were focused on. But we got a lot of data while we were out there, and some of them certainly were over channels. And I don't think that's really something we thought about, was trying to get that information out of it. So I'll have to chat with Atsu and see.
I mean, it's horrible to bring it in, but there's a fascinating analogy with issues that the hydrocarbons industry deals with, which is a thing called stress arching over hydrocarbon reservoirs when you deplete them and they sag at the surface, but are being sort of produced, eroded at the bottom, and it produces some really weird stress patterns, but they're imageable in seismic anisotropy at great expense, of course, and with easier logistics.
Yeah, and I suspect our data are too sparse to get a lot out of it, but I'll certainly talk with Atsu and see what he thinks. Yeah,
that's great. Smashing talk. Thanks very much.
Oh, thank you.
Okay, I have a last question. So looking at these images, it all looks pretty crevassed at the surface, right? So I assume you cannot just, I don't know, travel over these areas, but how did you actually manage to drill there if it's crevassed, or what is like the scale, you know, to the crevasses?
Yeah, so certainly I can find you a picture of Thwaites here. That was something that we were very aware of while we were out in the field, and we're being very, very careful about that sort of thing. We drilled up here, so kind of somewhere, I should know exactly, but somewhere in this area up here, and it was not. There were not surface crevasses where we were. So we were not able to, you know, go down in this area, and certainly couldn't do that. But we were able to, you know, bring radar lines across the channel and go up and down a little bit. With that, we had fabulous field guides that CC Mortensen and Blair Fife were with us, and they scoped all the routes first, roped together on ski-doos, and made sure that it was safe before we could go out and work on this. With our field team going out this year and watching these really big ones, our camp sits like right here, so it's headed towards that. So we're keeping a genuinely really close eye on this because we are seeing such rapid change on the eastern ice shelf. But yeah, the answer there is we didn't go where it wasn't safe, and there was enough room that was safe that we were able to work there.
What is a rough scale on this image? Like how far will it be from the crevasse?
Yeah, so let's see. So I should have a scale on there. I apologize. So from the kind of tip there to the channel, that's probably about 3 kilometers is kind of what we're looking at there.
Cool. Oh, that sounds really interesting. Nice. Okay. Any last minute questions? I'll just double check Facebook, but I think we have questions.
Well, thank you again so much for having me. I really appreciate it. It's super fun to share this stuff. And like I said, I'm happy if you got ideas, I'd love to hear them. I'm happy to chat more about this stuff later. So, you know, look me up and send me an email, and I'd definitely be happy to talk about it.
Well, thank you very much for a really fascinating talk, Karen. And yeah, see you all next week. Bye.